Okay, so welcome back, everyone. Let's begin with just a couple of announcements. Number one, somebody has asked here, when is the essay due, the writing assignment? It's going to be due. Yes, it's due on Wednesday, the 16th, December the 16th. Okay, so basically the last day when is our final? Is our final the 15th or the 16th? The 16th, right? So yeah. So when that day, the day of our final exam, by 11:59 p.m. that night, it's due. Okay. No, not the last day of class. Okay. If you have an issue getting it in on time, if for some reason it's late, then you can try submitting it late on Blackboard, or you can send me an email. All right, but try and please have it in on time on the 16th. Okay. If you're gonna have an issue, just let me know ahead of time. Will you lose points for lateness? If depends how late it is. All right. If you send it to me by the next day, that'll be fine. Okay. Okay. All right. So you submit it. So for the essay, you're going to submit it through Blackboard. Okay. If you look on the side, there's on the panel on the side, it says assignments. So if you click on assignments, you should be able to submit it through that. If for any issue you have some issue submitting it through Blackboard, then send it to me through email. Okay. But the email is your backup. You should send it to me through Blackboard. All right. Okay. If you have some issue with submitting it on time, again, just send me an email. Okay, and just let me know ahead of time, and we'll see if we can work something out. Okay. All right. Any other questions about that? Okay. Number two. The quiz that we were going to have today, we need the class time today. Okay. So instead of doing the quiz during class, what I'm going to do is I'm just going to post it on Blackboard later today, and I'll give you a couple of days to do it. You guys can go onto Blackboard whenever you want and do it whenever you have time. Okay. It's still going to be timed though. So whenever you decide to do it, you'll have like 20, 30 minutes to do it. Okay. You have to sit down in one shot and do it. All right. So is that clear to everybody? Is any questions on that? Okay. I just asked that again, that you don't work together when you're doing it. Just do it on your own. Okay. So
Professor,
class at some point later. Oh yeah. Go ahead.
and your voice, like on my end, was like cracking up. I didn't hear like half of what you said.
Okay, I'll repeat that. Yeah, I was going to repeat it. Okay. So again, the quiz that we were going to do today, it's not going to be during class time. Later today after class, I will post it on Blackboard, and I'll make some due date like in a couple of days from now. Okay, and I'll let you do it whenever you want, whenever you have time to do it. Okay. The only thing is it's still going to be timed though. So whenever you start doing it, you'll have like, let's say, I don't know, 20 minutes, a half hour to finish it, something like that. All right.
Oh, thank you.
Okay. No, it's going to be on Blackboard like it normally is. It just won't be during class time. Okay. I might split it into two quizzes, so we'll see. So there might be, you'll see maybe quiz 4 and quiz 5 just do both of them. Okay, whenever you have a chance. All right. Yeah, the last quiz would be the same. So what I'm going to do is maybe I'll split it into two quizzes, and that'll be quiz 4 and quiz 5. Okay. We take it after class. You can take it whenever you want. I'll probably make it due like by the end of the week, so you could do it any day that you want this week. Okay. No, quiz 4 and quiz 5. What I'm thinking of doing is I'll split chapter 4 into two quizzes. So you'll have two quizzes on chapter 4. Like one will be, let's say, 4.1, and the other will be, let's say, 4.2 and 4.3. Okay, something like that. Okay, I'm not going to give you a quiz on chapter 5. Chapter 5, I can't really quiz you on that. That's proofs, so I kind of need to see your work on that. Okay. Okay. Somebody's asking about the class after the final. So the schedule is as follows. We have class today. Wednesday, we have class on Wednesday as well. Okay. Next week, we have a final on the 16th. There's no classes after that. Okay, so our last classes are this week, and then next week's are the final exams. Okay, so there are no classes after the final. What chapters will the final be on? The final will be on chapters 4, 5, and 6. Okay, whatever we get to, whatever we have time for. Okay. Okay. Any other questions on that? Okay. All right. So one more thing I wanted to go over with you guys. We had missed a class. I had to cancel a class a little bit earlier in the semester. I want to make up that class this week, and I wanted to do it on Thursday, which I believe you guys should not have any classes on Thursday. It's supposed to be a reading day. I wanted to do it on this Thursday at about 3. So I want to do a makeup class because we missed a class earlier this semester. And I want to do it this Thursday, and I was thinking to do it Thursday at 3 o'clock. Okay. Does anyone have any issues attending that class if we do a makeup class on Thursday around 3 o'clock? Will it be recorded? Yes, it's going to be recorded. So if you do have an issue and you can't make it, that's fine. You can watch the recording. I'm going to put it up afterwards. Okay. Okay. Okay, that will be a review. What will it go over? It depends what we finish today on Wednesday. Okay, so we'll see what we do today and Wednesday, and if we finish everything we need to finish, then that class will be a review class. If not, then I might do a couple of extra things. Okay, so let's see what we did on Monday and Wednesday, and then we'll see what's left to do on Thursday. Okay, but again, I don't know yet what Thursday we'll be doing on Thursday until I see what we finish today and Wednesday. Okay. All right, so I'll post that on Blackboard just so everyone is aware of it. All right. Okay. If you want feedback on your essay, you can email it to me beforehand, and I'll try and take a look at it and let you know if it's good. Okay, or if there's anything you can improve if you want feedback. Okay, so if you want feedback, you send it to me through email. Don't submit it through Blackboard yet. Okay. 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 All right. All right, so let's get back to our classwork here. So hopefully we can finish up everything we need to do. So hopefully Thursday will be time for a review if we can get everything done by Wednesday. All right. Okay. Give me 1 second here. Yeah, I'm going to put an announcement on Blackboard. Okay, so you guys should be able to see this stuff there. I'll put it up hopefully later today. Okay. All right, so getting back to where we were last time. Last time we were in section 5.1. Okay, we were discussing induction. Okay, and we went through several examples of where we use induction. So again, induction is a method of proof. There are 2 steps. Okay. Step 1 is the basis step. And remember, in the basis step, you prove that whatever our propositional function is, P of n, you prove that P of n is true in the first case, okay, for the smallest possible value of n. And then we had our inductive step. In our inductive step, we prove the conditional statement if P of k, then P of k plus 1. We prove that that conditional statement is true. Okay, all right. All right, so that was induction. We discussed 3 different types of problems where induction can be used. We discussed using induction for summation formulas, or to prove that summation formulas are true. We talked about using induction to prove inequalities. And we talked about using induction to prove divisibility problems. Or divisibility results. Okay. All right. So any questions from the homework? I'm going to limit the questions from the homework today just because I want to save time for section 5.2. Okay. So if you have a homework question, I'll take 1 homework question now. And then if you had more questions, if you want, you can email me and we'll set up an appointment. I'll be happy to go over them with you. Okay. All right, so any homework questions? Today we're going to do 5.2, and then hopefully Wednesday we'll do some stuff in chapter 6. Okay, and whatever we get to, whatever we complete. All right. Okay, so I don't think there's any homework questions at the moment, right? All right, so let's move on to section 5.2 then. Okay. Again, if you have any questions, like I said, you can email me. We can set up an appointment. We can go over them together at some other point. Okay. All right, so today we're going to do 5.2, which deals with strong induction. So strong induction, again, is just a method of proof. It's very similar to induction with a little bit of a difference, okay? And the difference here is in the inductive step. Okay, the assumption that we make in strong induction, the inductive hypothesis, is different. Okay, but that's really the only change. Okay. All right. Okay, so strong induction is similar to induction. Okay. The only difference is the inductive hypothesis. Okay, so in the inductive hypothesis, okay, in regular induction, in the inductive hypothesis, we assumed that P of k was true. All right, and we proved that if P of k, then P of k plus 1 was true. In strong induction, we assume not just that P of k is true, we assume that every case up to and including k is true, and use that to show that P of k plus 1 is true. Okay. All right, so let me write it out as follows. Okay. All right. So to prove that P of n is true for all positive integers n, okay. Now the way I'm writing it out here, I'm writing it for positive integers, okay. But it doesn't have to be just for positive integers. It's for any set of integers. So the set of positive integers, the set of non-negative integers, okay, the set of integers greater than or equal to 10, doesn't matter, okay, as long as they're a set of infinite consecutive integers, all right, similar to what we did with induction. So to prove that P of n is true for all positive integers n, where P of n is a propositional function, we complete 2 steps. Okay, very similar to induction. So step 1 is going to be the basis step. Okay, in the basis step, same as induction, we verify that P of n is true for the smallest value of n. Okay, and if n is allowed to be a positive integer, then the smallest value of n would be 1. So in this case, we would be showing that P of 1 is true. Okay, if n was allowed to be any non-negative integer, then the smallest value of n would be 0. So we would show P of 0 is true. Okay. So again, the same thing as induction so far. Basis step is exactly the same, no changes. All right. And step 2 is the inductive step. Okay, so here's where the change exists. Here's where the change is. So the inductive step is as follows. We show that the conditional statement P of 1 and P of 2 and P of 3, dot, 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 all the way up to, oh, 1 second, up to P of K, implies P of K plus 1 is true for all positive integers K. Okay. So again, I wrote for all positive integers K, but K is allowed to be whatever n is allowed to be. So if n is positive, K is positive. If n is non-negative, K is non-negative. Okay, it's just by way of example, I'm writing positive integers. Okay, just to explain the idea. All right, so again, what's the difference? The difference is here. Okay, this is the conditional statement we need to prove. So how do we prove this conditional statement? Again, a direct proof, same like we did in induction. All right. The only difference is the hypothesis here, the inductive hypothesis. This part here is the change, okay? Instead of assuming that just P of K is true, we're assuming a lot more things are true. We're assuming that P of K is true, and every case before K is also true, okay? So we use that assumption to show that P of K plus 1 will also be true, okay? So we assume in this direct proof that we're going to do, we're going to assume that all the cases up to and including P of K, we assume they're all true, and show that if they're all true, then the next case, P of K plus 1, also has to be true. Okay. So any questions on that before I continue? All right. Now, why does this work as a method of proof? Similar to the way induction worked, okay? In the basis step, we showed that the first case was true. Let's say P of 1. We said P of 1 is true. What does the second, the inductive step, tell us? The inductive step tells us that if one case is true, then the next case has to be true. So in the basis step, we showed P of 1 is true. So by the inductive step, P of 2 also has to be true, all right? If the statements P of 1 and P of 2 are both true, they're both true, the inductive step tells us P of 3 has to be true. Next, the inductive step tells us if P of 1, P of 2, and P of 3 are all true, then P of 4 also has to be true, and so on and so forth forever. Okay, so do you see the difference between this and induction? In induction, it was that if 1 is true, then 2 is true. Then if 2 is true, then 3 is true. Then if 3 is true, then 4 is true, and so on and so forth forever. Here, it's if 1 is true, then 2 is true. Next, if 1 and 2 are true, then 3 is true. Then if 1, 2, and 3 are all true, then 4 is true, and so on and so forth forever. Okay, so in our hypothesis, in our assumption, well, then if 1 is false, then the proof doesn't work. Okay, then the proof is not true. Okay, that's why you need the basis step. You have to verify that the first case works. Otherwise, it's meaningless. All right. Okay. All right. So that's the idea. Any other questions on how this works before we see some examples?
Why do we use strong induction instead of induction?
Good question. Depending on the problem, the type of statement you're trying to prove, sometimes strong induction works better. Yeah, there are times when induction works better, and there are times where strong induction works better. Okay, it's not necessarily just sometimes one works and the other doesn't. Sometimes both will work. But one is easier to use than the other. Okay, the direct proof will work better sometimes with strong induction and sometimes with induction. Okay. All right. Let's see some examples. Okay, first example. All right. For this first example, we're going to prove the fundamental theorem of arithmetic that we did a while ago using strong induction. Okay, so show that if n is an integer greater than 1, then n can be written as the product of primes. Okay, that's the fundamental theorem of arithmetic. I've restated it here. Okay, that every integer greater than 1 can be written as the product of primes, right? Meaning either it is a prime or it can be written as the product of primes. Okay, so again, before we begin our 2 steps in strong induction, first it's always important to write down what is P of n, what is the statement we're trying to prove, and what is our domain, what is n allowed to be. Okay, so let's start by writing down what P of n is. Okay, so P of n here is the statement that n can be written as the product of primes. Okay. Also, whenever you're writing down what P of n is, make sure you have an n in the statement, because that's what you're filling in for n. Okay, that's your variable. It should be there. All right. What is n allowed to be? N is allowed to be any integer greater than 1. So n is an integer greater than 1. N is an integer, n is greater than 1. Okay, so that's our P of n, that's our domain. Let's now go on to the basis step. Okay, basis step. We have to show that the first possible value of n, the smallest possible value of n, makes the statement true. So what is the smallest value that n can be in this problem? What's the first case? 2, exactly. Okay. So we have to show that P of 2 is true. Okay. So let's start by writing down what P of 2 is. P of 2 is the statement that 2 can be written as the product of primes. Is that true? Yes, it's true, right? It's just a product of itself, right? So this is true. Right? Why? Because 2 can be written as the product of 1 prime itself, right? Because 2 is prime. Okay, so just write down 2, don't write anything else. It's a product of 1 number. Okay. All right. So this step is done. Now this, I meant to write this is true. This is true because 2 can be written as the product of 1 prime itself. Okay. All right, let's move on to the inductive step now. Okay. So what is the conditional statement we need to prove? We need to prove that the following conditional statement is true, that P of 2 and P of 3 and ... and all the way up to P of k implies P of k plus 1. Okay. So somebody's asking 2 equals 2 times 1. Should we ignore the 1? When I say the language maybe is a little confusing. When I say I can write 2 as a product of 1 prime, namely itself, I mean just write 2 as equal to 2. Okay. If it was 4, I would write it as 2 times 2. But if the number is already prime, just write it as itself. Okay. So you okay? Okay. So this is now the statement we need to prove. Okay, remember I'm starting at P of 2 because that's my first case, and I'm going all the way up to P of k. I have to show that this conditional statement is true. So in our inductive hypothesis, we're going to assume that this here is true, that the hypothesis here is true. So inductive hypothesis is as follows. Assume that P of 2 through P of k are all true. Okay, right? This is a direct proof. So we assume that the hypothesis is true. Okay. Another way of saying this would just be to say that P of j is true where j is a number between 2 and k. That's like a fancier way to say it if you wanted to say it that way. So you could also, that is, P of j is true where j is greater than or equal to 2, less than or equal to k. Right, for some integer k greater than 2. That's 2 times 2. I'm sorry if that's not clear. Right. I just meant that if it's composite, you will write it as a product of its prime numbers, right? So 4 is 2 times 2, 6 is 2 times 3, and so on and so forth. Okay. Okay. So any other questions up to this point? Okay. So what are we showing? We're showing that if it's true that I can write any integer between 2 and k as a product of prime numbers, then I can also write the integer k plus 1 as a product of prime numbers. That's what we're going to show now. So I'm starting by assuming that the inductive hypothesis here is true. I'm assuming that I can write any integer between 2 and k, including 2 and k, as a product of prime numbers. Okay? And if it's prime, you just write it as itself. Okay. All right. So next, we need to use this to show that P of k plus 1 is true. And what is P of k plus 1? Let's write that down. P of k plus 1 is the statement that the integer k plus 1 can be written as a product of prime numbers. Okay, so we're going to use the inductive hypothesis, that assumption that I can write any integer between 2 and k inclusive as a product of prime numbers. I'm using that assumption to show that I can write the integer k plus 1 as a product of prime numbers. Okay. All right. So there's really 2 cases. K plus 1, whatever integer that is, it's either prime or it's composite, right? It has to be one or the other. Okay. So there are 2 cases. K plus 1 is either prime or composite. Okay, let's examine them both separately. Okay, let's start with if k plus 1 is prime. Okay, if k plus 1 is prime, then I can write it as a product of prime numbers, right? Just write it as a product of itself. Write it as a product of itself. Okay. So that would mean that P of k plus 1 is true. Okay, similar to what we did for 2. Okay, just like 2 is prime. Okay. All right, so if k plus 1 is a prime number, P of k plus 1 is automatically true. If it's prime, just write it as itself, right? And you're done. Okay, and by when I write a product of itself, I don't mean k plus 1 times k plus 1. I mean just write k plus 1 as itself. Okay. What about if k plus 1 is composite? If it's composite, then that means that what? By definition, I can write it as a product of 2 integers, a and b. Right? If k plus 1 is composite, we can write it as a product of two integers, a and b, where one second. Yeah. Where a is greater than or equal to 2, which is less than b, which is less than k plus 1, well, less than or equal to. Like that. Okay. Okay. So again, if k plus 1 is composite, that means I can write it as a product of two integers. Let's call those integers a and b. Okay. Where a and b will be less than k plus 1, all right, and more than 2. Okay. So in other words, k plus 1 is more than b, which is more than or equal to a, which is more than or equal to 2. Yeah. The double arrow usually just means like then or therefore. Okay. Okay, any questions on this part? Okay, this just comes from the definition of composite number. Okay. Okay, so what does this mean? This means that a and b are both integers between 2 and k, okay? A and b are both integers greater than or equal to 2, but less than or equal to k. Right, a is somewhere between 2 and k, b is somewhere between 2 and k. All right, do you follow me on that? Do you agree with me on that? Yes. Okay, great. All right. So what do I know about A and B? All right, if I go back to look at my inductive hypothesis for a moment, I'm just going to scroll back up for a moment. We had assumed in our inductive hypothesis that for any integer between 2 and k, including 2 and k, I can write those integers as a product of prime numbers. That's our assumption. Okay. So using that assumption now, a and b are both numbers between 2 and k. So by our inductive hypothesis, we can write a and b as a product of prime numbers. Okay, so by the inductive hypothesis, a and b can be written as a product of prime numbers. Okay, so this is the step where I'm using the inductive hypothesis, where I'm using my assumption from before. Okay, since a and b are both numbers between 2 and k, they fall into the inductive hypothesis. They're integers between 2 and k. I can write them as a product of prime numbers. Okay. So what do I know? I know that k plus 1 equals a times b. A and b can both be written as a product of prime numbers. So if k plus 1 is composite, it's a times b. I can write it as a product of primes by writing it as the product of primes that make up a times the product of primes that make up b. Okay. So thus, if k plus 1 is composite, meaning k plus 1 equals a times b, okay, it can be written as the product of primes namely those primes in the factorization of a and those in the factorization of b. And with that, the inductive step is done. Okay, so again, just to review what we just did. Okay, if k plus 1 is a composite number, I can write it as a times b, where a and b are both numbers between 2 and k. All right. By the inductive hypothesis, a and b can be written as a product of prime numbers. So how do I write k plus 1 as a product of prime numbers? I just do the prime factorization of a. I write a as a product of primes times the prime factorization of b. So I write b as a factor as a product of primes. Okay. And that concludes the inductive step. We showed that k plus 1 can be written as a product of prime numbers. So the proof is done. Once the inductive step is done, the proof is done. Okay. Okay, so questions now. Let's see. How is this a proof when we did not even prove our assumption numbers greater than 2 can be written as primes? Okay. Well, that's what the proof, so to speak, does. Okay. Any number greater than or equal to 2 is either going to be a prime itself, okay, in which case you're done, or if it's composite, then the proof tells you what to do. All right. Okay. So in other words, you're asking me, is it necessary to validate our assumption? No. All you need is the basis step. Once you have the basis step, you're done. You're good. Okay. So in other words, you need the basis step. You need to show that the first case is true, and you need to show that as long as all the cases, when all the cases up to k are true, the next one is true as well. Okay. All right. Any other questions on this problem? Okay, let's do another example. Okay. Anyone here familiar with the game of NIM? N-I-M. Nope, never. Some of you may have heard of it before, maybe not. Okay. All right, so the next problem is a variation of the game of NIM. All right, so consider a game in which two players take turns removing any positive number of matches they want from one of two piles of matches. Okay. The player who removes the last match wins the game. Okay. All right, so let's understand the game before we continue with the question. Okay. So imagine you have two piles of matches. Okay, it doesn't have to be matches, it could be marbles, could be candies, whatever you want. Okay. There's two piles. Each pile has some positive number of matches. Okay. There's two players. The players take turns. On your turn, player A's turn, let's say they're player A and playing player B. On player A's turn, he can take as many matches as he wants. He has to take at least one. Okay. He can take as many matches as he wants from any of the two piles. Okay. But on his turn, he can only take from one pile. He can't take from both. Okay, so he picks one pile he wants to take from, and he has to take some positive number of matches from that pile. Then the second player goes, let's call him player B. He picks any of the two piles, and he has to take some positive number of matches from that pile, any number that he wants. But he has to take at least one, and if he wants, he can take all the matches in that pile on his turn. Okay, but again, he can't take from both piles at the same turn. All right, and then the first player goes again, and he picks one of the two piles and takes some positive number of matches from that pile, and so on and so forth. They keep going until no matches remain. Whoever gets the last match wins. All right. Okay. So the question is as follows. Show that if the two piles contain the same number of matches initially, the second player can always guarantee a win. Okay, so we're going to show that if the two piles contain the same number of matches initially, let's say we start with both piles having, let's say, n matches, okay, then the second player can always guarantee a win, and the second player will win. Okay, that is if he follows a winning strategy. Okay, and by doing the proof here, we're going to have to come up with what the winning strategy is. All right. All right, so in other words, we're basically showing that this is a rigged game, that if you know the strategy and you're player number 2, you will win. All right. Okay, so first of all, before we begin the proof by strong induction here, what is P of n? Okay, we have to figure out what P of n. What is the statement that we're trying to prove is true? So P of n, right? Hopefully, if you think about it for a moment, you'll be able to figure it out. But the statement we want to prove is the statement here, that if the two piles contain the same number of matches initially, the second player will win. So I have to stick in the variable n in there, so I'm going to write it as follows. If both piles contain n matches initially, right at the start, the second player can always guarantee a win. Okay, so I basically just copied down the statement. I stuck in the variable n there. Okay. What is the domain here? Well, to have a game, we have both piles have to start with at least one match. Okay, so n will have to be greater than or equal to 1. In other words, n has to be a positive integer. Okay, so n is a positive integer. Right? Okay, so that's P of n, and that's our domain. Okay, any questions before we continue? Okay, so we go to the basis step first. Basis step. Okay, the smallest value that n can be in this problem is 1, so we have to show that P of 1 is true. Let's write down what the statement P of 1 is, so we know what it is we're trying to show is true. P of 1 would be the statement if both piles, and I may rewrite the sentence in different ways throughout this problem. Okay, let me try and keep it the same though. If both piles contain one match initially, the second player can guarantee a win. Okay. Is that statement true? In this game, we're starting with both piles we're starting both piles with one match. Will the second player win? Yeah, that's true, right? And hopefully that's obvious to everybody if you think about it for a second, right? You have two piles, each with one match. Player one goes. He has to take at least one match, and he's only allowed to take from one pile. So he takes one match from one pile, leaving only one match in the other pile. So the second player will take that match and win. Okay? So is that clear to everybody? Okay, so the second player wins in this case. All right, this is true. Okay, and let's maybe write that out quickly. The first player will take, must take one match from one of the piles. Okay. And the second player takes the remaining match for the win. Okay, that's what has to happen. There's really no other options, okay? So now let's move on to the inductive step. The basis step is done. We showed in the first case, when n equals 1, when both piles have one match initially, the second player has to win. Inductive step. Okay, so in the inductive step, what's the conditional statement we want to prove? So we're starting with n equals 1. So the conditional statement we want to prove is that p of 1 and p of 2 and dot, 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 all the way up to p of k implies p of k plus 1. Okay, we want to show that, wait, let me write it over here. Show that this conditional statement is true. Okay. So inductive hypothesis. We assume a p of 1 through p of k are all true. For some positive integer k. Let me write it this way. Okay. If you want to write it the fancy way that I did before, you assume that p of j is true for j greater than or equal to 1, less than or equal to k. Okay, so that's our assumption. We're assuming that that's true. We're going to assume, we don't know that this is true. We're assuming that it's true, that for any integer between 1 and k, okay, if our two piles start with that number of matches initially, for any number between 1 and k, that the second player can guarantee a win. Okay, so we don't know that that's true. We're just going to assume that it's true. Okay, so if k is 25, then we're assuming that for any number between 1 and 25, including 1 and 25, if I start with both piles having that number initially, the second player will win. Okay. Could I go up for a sec? To what? What would you like me to go up to? I'm sorry. Back to the basis step? Yeah, okay, sure. Okay, so any questions so far on what the inductive hypothesis is? Okay, so we assume that the hypothesis is true. So we assume that for any case between 1 and k, including 1 and k, that the second player will win. Okay, so if I start with any number between 1 and k, player 2 will win. I'm assuming it's true without knowing it's true. I'm just assuming that it's true. Okay. All right, next we need to show, so we need to use this assumption, use this to show that P of k plus 1 is true. What is P of k plus 1? Let's write that down so we know what it is we're trying to show is true. That's the statement that, and again, whatever P of n was, I just replace n with k plus 1. So that's the statement if each pile starts with k plus 1 matches, the second player will win. Okay, I paraphrased it. More or less, that's what I said before. Okay, so that's what we want to show is true, using our assumption that 1 through k are all true. Okay. Okay, so this is how we're going to do it. Okay, assume that we have our two piles here. Okay, let's say that's pile 1, that's pile 2. Here's pile 1, here's pile 2. Okay, each one has k plus 1 matches in it. Okay, the first player will go. Okay, so the first player will take, he's going to take some positive number of matches from one of the two piles, right? How many he's going to take, I don't know, but he's got to take some positive number. So the first player will take, let's say, R matches from one of the piles. Okay, and where R is some number greater than or equal to 1, less than or equal to k plus 1, right? He has to take at least one match, and if he wants, he can take all the matches from one of the piles. Okay. Okay, good. Any questions so far? Okay. So first player goes, he takes R matches from one of the piles. Let's say he took R matches from the first pile, from pile 1. How many matches are now left in pile 1? Okay, so if you had k plus 1 matches, the first player removes R matches. How many are left? Exactly. K plus 1 minus R is the amount that's left in that pile. Okay. Okay. Leaving k plus 1 minus R matches in that pile. Okay, so if you want to see the diagram again, let's say pile 1, pile 2. Here will be k plus 1 minus R. Here will be k plus 1. Okay. All right. Now, k plus 1 minus R, hopefully you'll agree with me, is some number, it's got to be some number between 1 and k plus 1. Okay. Actually, let me write it this way. It's got to be some number between 1 and k. Do you agree with me on that? He had to take at least one match. Okay. All right, so that's the amount of matches that will be left, and it has to be some number between 1 and k. Okay. Give me one second. Give me 1 second. I'm sorry, just. Okay. All right. Sorry about that. Where are we here? Good question. Well, let's see. If player 1 takes all of the matches from one pile, okay, let's say he takes k plus 1 matches. Would that be a smart move? Why would he not want to do that? If he did that, then what would player 2 do? He would just take all the matches from the other pile and win, right? So he wouldn't want to do that. Okay. All right. Okay. Okay, so we're going to assume that he's not going to take them all. If he does take them all, then he loses, and player 2 wins. So that's fine, okay? Player 2 will win, and it's fine. That's what we want to show anyways, that player 2 will win. So let's assume that he's not going to take them all, and he has to take at least one. So how many will be left? Some number between 1 and k. All right, my question to you now is, what should player 2 do in his next move now, in order to guarantee his win? How many matches should he take, and from which pile should he take them to guarantee his win? Okay, so you're looking at the 2 piles. Player 1 took R matches. So pile 1 now has k plus 1 minus R matches. Pile 2 has k plus 1 matches. The question is, what should player 2 do? How many matches should he take, and from which pile, in order to guarantee his win? What do you guys say? All right, so while you're thinking about it, let me give you the answer, okay? What happens if player 2, the second player, player B, whatever we want to call him, let's say he takes the same number of matches, R matches, from the other pile, okay? So let's say let player 2, or let the second player also take R matches, but from the other pile. So he's going to take the same number of matches that the first player did. He's going to mimic him, but he's going to take them from the other pile. So now how many matches are in each pile? This one has k plus 1 minus R, and the other one also has k plus 1 minus R. So they both now have the same number of matches, okay? And each pile has some number of matches between 1 and k. And the first player, player 1, is about to go. Okay. So by my inductive hypothesis, right, what was the inductive hypothesis? The inductive hypothesis told me if I have 2 piles with the same number of matches, who's going to win? Right, we had assumed at the beginning. Yeah, exactly. In our assumption, in our inductive hypothesis, we assume that if I have 2 piles with the same number of matches, okay, the second player will win, as long as I'm between a number between 1 and k. Right now, k plus 1 minus R is a number between 1 and k, and both piles have the same number of matches. So by the inductive hypothesis, player 2 has to win. Okay? All right. So, so both piles have the same number of matches, right? Namely, k plus 1 minus R, and k plus 1 minus R is some number between 1 and k. So by the inductive hypothesis, player 2 will win. Okay. We assume that that was our assumption. If I've got some number between 1 and k, and both piles have the same number of matches, the second player will win. That's what we now have. We reduced to a case that was included in our inductive hypothesis. So player 2 will win, and the inductive step is done. We showed that when you have k plus 1 matches in each pile initially, the second player will win. How? By just mimicking whatever the first player does, okay, with regards to the other pile. The inductive step is done, and the proof is done. Okay. All right. Any questions on that example? Yeah. Okay. All right. So again, in the basis step, we showed that when both piles start with 1 match initially, the second player will win. Okay. What have we done in the inductive step? In the inductive step, we have to show that if P of 1 through P of k, if those cases are all true, we assume that those are true. If those cases are all true, then the next case, P of k plus 1, also will be true. Okay. That's what we did here. We started with k plus 1 matches in each pile. Okay. We're assuming that, again, if I have 2 piles and both have the same number of matches, and that number is some number between 1 and k, then who will win? The second player will win. Okay, so if I've got 2 piles, each has k or less matches, then the second player will win. Okay, so now if I've got k plus 1 matches in each pile, player 1 goes, he takes some number of matches from the first pile. Okay, so let me give you some numbers maybe to make it a little bit more clear. Let's say that k plus 1 is 10. All right, so I'm assuming in my inductive hypothesis, so let's say k is 9. Okay, I'm assuming in my inductive hypothesis that if I've got initially any number between 1 and 9 in both piles, player 2 will win. So now if I've got 10 matches in each pile, okay, that's the k plus 1. First player goes, let's say he takes 3 matches from the first pile. So that leaves 7 in that pile. The second player goes, he should do the exact same thing but to the other pile. Let's say he takes 3 matches from the other pile. So now both piles have 7 matches. 7 is a number between 1 and 9. So I've got 2 piles with the same number of matches, and that number is a number between 1 and 9. So by that assumption that I made at the beginning, as long as I was a number between 1 and 9, both piles have the same number of matches. Player 2 will automatically win. Okay, so I went from k plus 1 to a number between 1 and k. Okay, I reduced from k plus 1 to some number in my inductive hypothesis, to a number between 1 and k. Okay, and that's really what a lot of these problems do. You got to go from k plus 1 to something in k. I mean, something between 1 and k, I should say it that way. All right. Let's do one more example today of this. Okay. Before we do the next example I want to do requires us to use a slightly modified version of strong induction. Okay. So let me give you this modified version of strong induction first, and then we'll do the example. Okay. In this modified version that I'm about to give you, the only difference is in the basis step. The quiz, as I said at the beginning, let me repeat it. The quiz is not going to be during class. Later today, I will post it on Blackboard, and you can do it whenever you want. It'll still be timed. So whenever you start, you'll have a limited amount of time to finish, but you can start it whenever you want. Okay. And I'll give you till the end of the week to do it. Okay. I'll probably make it like Thursday or Friday or something like that. Okay. All right, we'll see. We'll see about the deadline. Okay. All right. There's a question here about how strong induction works. I don't have so much time right now to deal with it. Maybe on Wednesday if you want to ask your question again. Okay, or you can send me an email. Either way. Okay. All right. Okay, so let me give you this modified version. So in this modified version that I'm going to give you now, as I was saying, the difference is going to be in the basis step. Okay, in this basis step, instead of just proving that the first case is true, sometimes it's necessary to show that the first several cases are true. Okay, so this is what I'll call a modified version of strong induction. Okay, so to show that P of n is true for all integers n, well, let me write it, for all integers n, with n greater than or equal to b, we complete 2 steps. Step 1, the basis step, and this is where the change is, as I said. Verify that P of B plus 1, ... all the way up to P of B plus J are all true. Okay, so you're not just showing that the first case P of B is true, you're showing that the first several cases are true. okay, from P of B up to P of B plus J. All right. Yeah. I think those letters are chosen just for reference to peanut butter and jelly, but okay. Step 2 would be the inductive step. And in the inductive step, we show that the conditional statement, if P of B and P of B plus 1 and P of B plus 2 and dot, 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 and all the way up to P of K. If those are all true, then P of K plus 1 is true. Okay. We show that this is true. This conditional statement is true for every integer. Okay, and here's the other change. For every integer K greater than or equal to B plus J. Okay, so K, in other words, K starts wherever the basis step stopped. Okay, so K has to be greater than or equal to B plus J. All right. Can I go up? What would you like me to go up to? Is that good? Or... Yeah, okay, great. Okay. So let me give you the question now. I'll say it over first and then I'll write it down. So the question is as follows. Prove that every amount of postage of 12 cents or more can be formed using just 4-cent and 5-cent stamps. Okay. So prove that every amount of postage can be formed using just 4-cent and 5-cent stamps. Oh, I have to prove that every amount of postage of 12 cents or more. I forgot that part of postage of 12 cents or more. I forgot that. Okay. Prove that every amount of postage of 12 cents or more can be formed using just 4-cent and 5-cent stamps. Okay. All right, so in other words, another way of phrasing this would be that every integer greater than or equal to 12 can be formed by some combination of 4s and 5s. Okay. All right. So first of all, what is P of n in this problem? Okay. So P of n is going to be the statement that postage of n cents can be formed using just 4-cent and 5-cent stamps. Right. So for example, let's say you go to the post office, you want to send a letter. They tell you this letter is going to cost you 30 cents worth of stamps. You say, okay, what kind of stamps do you have? So they tell you we have 4-cent stamps and 5-cent stamps. Okay. So can you buy enough 4-cent and 5-cent stamps to get exactly 30 cents? Okay, so this is saying yes. For any number greater than or equal to 12, you can get to exactly whatever number you want using just multiples of 4 and 5 combined. Okay, what's the domain here? N is some integer greater than or equal to 12, right? N is at least 12 cents. Okay, so in our basis step, okay, in this problem, this is our modified version. So we're not going to just show that P of 12 is true. In this problem, we're going to show that actually that the first 4 cases are true. and I'll explain why in a minute, but let's do it first. Okay, so verify that the first 4 cases are true. Right? Those are P of 12, P of 13, P of 14, and P of 15. Okay. Okay. Let's start with P of 12. That's the statement that I can form 12-cent stamps using just 12 cents worth of postage using just 4-cent and 5-cent stamps. So can I get 12 using just 4s and 5s? Let's see. Yeah, just use 3 4-cent stamps. Okay. Can I get 13 using just 4-cent and 5-cent stamps? Yeah, use 2 4-cent stamps, which will be 8 cents, plus 1 5-cent stamp. So 2 times 4 is 8, plus 5 is 13. What about 14? For 14, I use 1 4-cent stamp, plus 2 5-cent stamps, right? 2 times 5 is 10, plus 4 is 14. And for 15, I just use 3 5-cent stamps. Okay. All right. Now, what about for 16? Okay. I can do 16 as well. I just add another 4-cent stamp, or I do 4 4-cent stamps. Okay, and so on and so forth. Okay. But I don't need to show that. I only need to show the first 4 cases. Now, why the first 4 cases? Why in this particular problem am I only doing the first 4 cases in the basis step? Okay. So the reason why is if I go back to the question, I'm allowed to use two types of stamps, 4-cent and 5-cent. Now, the reason I'm only proving the first 4 cases is because the smallest type of stamp I'm allowed to use is a 4-cent stamp. Okay. So because the smallest one I'm allowed to use is a 4-cent stamp, I'm showing the first 4 cases. Hopefully that'll become a little bit more clear, again, why I'm doing that when I do the inductive step. Okay. All right. So let's move on to the inductive step now. Okay. Okay, so in this step, we need to show that P of 12, that's our first case, and P of 13, and ... all the way up to P of k implies P of k plus 1. We have to show that that conditional statement is true. Okay. For some number k, where k is greater than or equal to 15. Okay. K starts where we stopped in the basis step. So in the basis step, we stopped at 15. So k has to be greater than or equal to 15. Okay. Okay, so what is this saying? This is the conditional statement we need to prove. We're going to do a direct proof. So we assume the hypothesis is true. So inductive hypothesis. Y greater than or equal to 15. That's the way that this modified version works. Okay. I've already shown that I can do it up to and including 15. Okay, so k will start from there. All right. Like in my basis step, I already showed that I could do up to and including 15. So for the inductive step, I already showed those. So now I'm just going to go from those and higher. Okay. All right. Inductive hypothesis. We assume that P of 12 through P of k are all true. Okay. In other words, what is that? What am I saying? In other words, I'm going to go over just another minute or two, and we'll reach the end of this problem in just a minute. I'm just going over time, but just a little bit today. So in other words, what is it we're assuming is true? we assume that we can form postage of J cents using just 4-cent and 5-cent stamps where J is some number between 12 and K. 12 and K. Yeah. Okay. So again, that's our assumption. Starting with any number between 12 and K, we assume that I can get that number by some combination of 4s and 5s. Okay, so anything between 12 and K, we assume we can do. Okay. So we need to use this to show P of K plus 1 is true. What is P of K plus 1? Let's write that down. So P of K plus 1, that's the statement that we can form K plus 1, a postage of K plus 1 cents, using just 4-cent and 5-cent stamps. Okay, so that's what we want to show is true, and at some point we're going to use our inductive hypothesis, okay, along the way. All right, let's say I start with K plus 1 cents, okay? That's the postage I want to form. All right. Now let's say I use, let's say I use 1 4-cent stamp, okay? So let's use 1 4-cent stamp. That's what we're going to use initially. All right, you're at the post office. You ask them for 1 4-cent stamp. How much is left? Okay. How much postage is left that you need stamps for? Well, it's K plus 1 minus 4 is left, which is going to be K minus 3. Yeah, exactly. Okay, so you need to do K plus 1. So you ask the guy at the post office, you say, give me 1 4-cent stamp. So how much is left? It's K plus 1 minus 4, which is K minus 3. Okay. K minus 3, hopefully you will agree with me, is a number less than or equal to K, right? K minus 3 has to be less than that, and it's greater than or equal to 12, right? Remember, K is at least 15, so K minus 3, the smallest it can be is 12. So K minus 3 is a number between 12 and K. Okay, so therefore, K minus 3 is a number between 12 and K. That means it fits into the inductive hypothesis. Remember what I said before? We're always trying to reduce to a number less than or equal to K, right? So K minus 3 is a number between 12 and K. By the inductive hypothesis, we can form postage of K minus 3 cents using 4 and 5-cent stamps. Okay. So how do I get to K plus 1? Just use the formation for K minus 3 and add 1 more 4-cent stamp and you get K plus 1. So use wait, let me write it this way. Add 1 4-cent stamp to the postage, well, to the stamps for K minus 3 to get K plus 1. And we're done. Okay, so how do I form k plus 1? Just form k minus 3. How do I know I can form k minus 3 postage using 4-cent and 5-cent stamps? I assume that I could. Okay, whatever number that is, just add one more 4-cent stamp and I get k plus 1. All right, and we're done. Okay, so that's it for today. I'm sorry for going over a little bit. We'll stop here. We'll then take attendance. Okay, thank you for staying a little late. If you have any questions, I'm here for a few minutes. And I will see everybody on Wednesday. Okay, I'm going to post the lecture and some homework on Blackboard as well as the quizzes. Okay. Yeah, it takes a little time for to upload onto the Google Drive, but once it's ready, I'll post it. Okay, I'll try and get it tonight if I can. The quiz, it'll be due in a couple of days. Maybe I'll make it due during the weekend or something like that. We'll see. All right, I'll put details about it on Blackboard also, so you can look there. We had a question here. Is it okay if we use the 5-cent stamp initially instead of the 4-cent stamp? Well, yes, but with a condition. You then in the basis step, you would have had to show that the first 5 cases are true. Okay, so it just makes it you have to do more work. Okay, all right, everybody. I'm going to assume everybody wrote their name for attendance. I'm going to head out. Have a good night, everybody. Take care.